Do you see again the screen?
Yes, we can see your screen, and we are actually now live and being recorded. So welcome, everyone. Welcome everyone to our third day of the Gaia Science Alerts workshop. It's the 11th OPTICON Gaia Science Alerts workshop, and we do it online, as many things these days. But thanks to this, we can have, I think, impact, and we can connect with a much broader community than we normally have at our meetings. So there are advantages of these disadvantaged times. Today's session will be, another interesting session with a variety of topics. And we begin with Nami Maulavi from University of Geneva, Switzerland, who will tell us about variable objects processing in Gaia consortium. Nami, I will give you a warning at about 18 minutes after your talk, so that you're left with 2 more minutes to wrap up, and that will give us 5 more minutes for discussion and question. Okay, Nami, please.
Okay, thank you, Łukasz, and good evening, afternoon, morning, wherever you are, to everybody. So I will give an overview of the variable object processing within the Gaia consortium. This is, of course, on behalf of many colleagues in Geneva, my colleagues in Geneva, or at other places in Europe and even beyond, within the Gaia Data Processing and Analysis Consortium. I will do a short introduction and then detail the processing steps within the Gaia consortium, and end with another part about the variability studies in the Gaia archive. And I want first to stress the extraordinary times in which we live now for the research in variable objects. And to have a step back, let's remind that the first variable stars that were observed in the sky, at least to the records we have, are now almost 2,000 years old, but just a few guest stars in the Chinese records. And then it's a few centuries ago where it was started with supernovae, the Tycho and Kepler supernovae, of which you see images of today, of course, on the upper right. And the next ones are just a few years later with the famous Myra, which has a pulsation of 7 magnitudes, which is really huge, which makes it appear to visual eyes at some times, but then disappears for quite some time. And the first time it was actually observed, people thought that it was one of those supernovae or guest star that appears, and that would be the end of it. But actually it reappeared, and 2 other Myras were detected not long thereafter. Another famous variable star was the Algol eclipsing binary, which has a 1 magnitude variation in the visual in the late 70s. And then another famous star is the Delta Cephei, which has become the basis of the class of variables on the distance determinations in the universe from about 1 magnitude. So by the end of 18th century, we knew about 10 variable stars. Now, if you looked carefully, actually, there were already 3 distinct classes of variable objects which were observed in this. And there were the pulsation ones with the Myra and the Delta Cephei. You had cataclysmic variables, which is certainly a main object of discussion in this workshop. And then you have the eclipsing binaries, which were observed. These 3 types, distinct classes of variables, are only a part of several ones, which are the eruptive ones, eclipsing stars from themselves, rotation, eclipses due to another object, microlensing, secular variability, and you globally can identify them under a variability tree which has intrinsic variability and extrinsic variability for variations that are due not to the star itself that is observed, but to something which is out about itself, whether other star around itself in binaries or further away. Now, in each of these groups of variability types, you have a plethora of different variability detailed types. You have the pulsation ones, cataclysmic ones, eruptive, Arcturus borealis, for example, for the single star eclipses, and so on. And the full challenge of variability studies is to be able to not only detect them, but also to recognize them, classify them, which then will allow to study their properties in more detail. In the last decades, the pioneering photometric large-scale surveys were conducted by the surveys which targeted microlensing searches for the machos in the galaxy, and these were the Eros, Macho, and Ogle large-scale surveys in the beginning of the 90s. And the field grew until recently, and it's continuing to grow. And in the recent years, the number of variables that have been reached by the different surveys and these are only the recent ones for the last few years, we reached hundreds of thousands of variables detected, almost 500,000, 1 million with Ogle 4, AVSO with amateur astronomers, they record as a whole 1.5 million, and DTF reached 10 million stars, and so on. The list is not exhaustive, but it shows how productive this field is becoming. It also shows that for a given survey, the way you consider variables and the detection sensitivities will lead to different numbers of variables. For example, in ZTF, the analysis of the periodic variabilities in the data release 2 led to about 500,000 detection. But if you take the full sample of even in data release 1, you can reach up to 10 million variables. With Gaia, since this is the object of the talk here, data release 1 about 5 years ago was leading just a few thousands to show the capability of Gaia to detect the variables and the type of light curves it can produce. 2 years ago in DR2, we published about 500,000 variables. And these are in variability catalogs, meaning that the classification identified specific types of variables, and a subset of those ones we decided to publish in DR2, and that led to 500,000. If now you go back to the full data release 2 sample, even by selecting only large amplitudes, typically larger than 0.2 magnitude, you reach already about 20 million, and that's only the large amplitudes ones. So for the future, for data release 3, we expect to have about 7-10 million, that's next year, 7-10 million variables published in specific catalogs. And in DR4, that's several years later, we can expect to have more than 100 million stars. Future will also be we'll also see other surveys coming, such as the LSST, now called Vera Rubin Observatory, which will lead to an explosion of the number of variables detected as well. And we are really in a very specific time of astronomy for variable stars. Now, I should say when you have these large surveys, I would say it's relatively easy to detect and publish variable objects. It's much more challenging to publish a catalog which you can master the quality, typically of how many contaminations you have and what is the purity of the catalog. And the whole purpose of studying and publishing a catalog would be to increase the quality of their content. So let's have a look now at the Gaia consortium, which leads to the publication of the data and in particular variable stars. So you have heard, and it's the object of this workshop, how the Gaia Science Alerts are producing on a daily basis alerts on variables that occur at a daily in a near real-time processing within a maximum of 2 days delay, and that targets sources that would require immediate follow-up for scientific return, and that's what you have currently seen. Within the consortium, there is a very large team which has been set up since more than a decade, and that has been divided into several what we call coordination units, each of them having a specific purpose in the processing of the data. And just to give a short summary of the different coordination units that are available, you have the coordination units 5, which is a basic photometric processing, which calibrates the G band, BP and RP spectrophotometry. CU6, which goes through the spectroscopic reduction and analyzes the RVS spectrometer for spectroscopy and provides the radial velocities that are being published. CU4, which treats non-single stars, solar system objects, extended objects. Then you have the CU7, variability processing, which I will talk more about in the next slides. And together with it, we have a data processing center, which is also in Geneva. There are many other data processing centers. I mentioned this one specifically because it is dedicated to the processing of the variable objects. And it is also located in Geneva, where the core team of the CU7 is also located. And actually, the fact that these two centers, Coordination Unit 7 core and the Data Processing Center are at the same place gives a huge benefit to the interactions between these two entities and the resulting efficiency of data processing. You have CU8, which deals with the astrophysical parameters, which takes the data, spectroscopy and other photometry and other data, and gets the stellar parameters, interstellar extinctions, and parameters like these ones. You have CU9, which arranges all the necessary implementations and design for the Gaia archive, which would then lead to the Gaia archive in ESA that the scientific community is accessing, that you all and each of you are accessing. So let's now go a little more in the detail of CU7 variability, and there are many interactions between each of these CUs, one and another, and all together. I just show here a summary of the processing that deals with the variability processing related to CU7, where for DR2, as an example, the data flow went from CU3 for the astrometry, parallax, proper motions, and from CU5 for the calibrated G, GBP, and RP color photometry, which we use in our variability processing, the result of which are variability tables that are given to CU9, which feeds the Gaia archive at ESA, and which you have accessed since 2 years ago for the DR2. Variability types that were published in 2018 for DR2 by CU7 concern Cepheids or Lyrae, long period variables, rotation modulation variables on the main sequence, delta Scuti as 6 Finis stars, and short time scale variables. And I will tell a little more about these ones just a few slides later. For DR3, which is due for next year, and we are still in the process of building it and doing it, we have, in addition to what was processed in DR2, we also use the red photometer spectra and radial velocities for part of our processing to deliver similar types of data in the variability tables. But of course, that would include many more types than the ones that we published in DR2. And if I have to see much further away for DR4, then we can use the full set of data, which includes the radial velocity spectrometer spectra, probably, but at least the BP spectra as well, and the astrophysical parameters that come from CO8. This overview also shows something inherent to the processing throughout the consortium. The way the consortium works is through cycles of processing. We have 6 months cycles of processing where each of the coordination unit processes the data and then feeds to a main database within the consortium that the other CUs can take from and provide their own processing. As a result, it makes a little problem. I mean, in DR2, we all have to publish the results of our processing, but we could not necessarily get the latest version of the previous CU processing. For example, in our case, we would not be able to get the radial velocities on time because they would just produce it. And that led in DR2 for some data to be shifted to be not in phase with the data, full data that is published in DR2. For DR3, this problem is partly alleviated by the fact that we had an early data release for part of the data, which is basically the astrometry and the photometry. And next year, the other CUs can process these ones and publish them with some delay, but at least in a consistent way with the other data. Within the CU7 now, let's go in the CU7. We have data coming from CU5. I show here the example of data release 2, where we have a basic pre-processing of the time series, some statistics which are computed on the time series. And then we have a first big box of general variability detection, which uses machine learning techniques. In DR2, that was mainly a random forest to identify variables in contrast to constant stars. And we also have a special variability detection module, which goes beyond and for some specific types, goes directly to the initial time series to identify the variables. This was, for example, the case for short time scale variables, which used actually the CCD level photometry to identify the short time scales. Okay, and once we have the variable candidates, there is a module of characterization that, among others, find the periods of in the time series, tries to fit a model to the light curve, and feeds to the classification module, which is another main step that uses machine learning techniques to provide variability types. Some of them would then go to specific modules for specific object studies, for example, Cepheids, long period variables, or Lyrae, that would take these variable types and provide a cleaner set, purity-oriented catalog, which would then be validated before being sent to the main database at ESAC. This is purity-oriented. However, of course, we would lose some stars, some variables that would be of correct types, but which would have been filtered out by these specific object studies. So we also publish in parallel classification catalogs, which are completeness-oriented, and that also feed the main database. Purity versus completeness is always a challenge that we try to overcome, and the approach we have taken for DR2, and we will also take for DR3, is to publish two types of variability catalogs. One SOS oriented for purity, and the other one from classification that have more stars, completeness, but the purity might be less complete. Okay, for DR3,
2 more minutes.
For DR3, what 2 more minutes?
That's right, yes.
Isn't it 25 minutes?
Well, with questions, but well, you can use up all the time, but there will be no time for questions.
Okay.
Go ahead, continue.
So for DR2, this is a summary of the various types that were published for the different types in classification and in SOS. And this is one example of the completeness and contamination study that we did for DR2. Now for DR3, these are some types of examples of variables that we plan to publish. I just show you that will be for next year. One thing to mention as well is that we will have in DR3 the Gaia Andromeda photometric survey, for which all sources, constant and variables, will have their time series published. This is an example of the HR diagram that we get given the simultaneity of the different instruments. In the HR diagram, you have the absolute luminosity, the temperature, and you see here how with the day that is going on here, you see 150 days after the start, how the different stars, long period variables, for example, they move in this HR diagram. That's really variability seen in the ice. Okay. A next movie that would show for DR3 and illustrates the combination of astrometry here, the photometry, the color BP minus RP, and the spectra, RP spectra, which shows how long period variables, they move in this HR diagram. And you see the different RP spectra that are also changing with time. And with this is the same for a carbon-rich star. And if you were careful, the spectra of the oxygen-rich and carbon-rich stars have different patterns. And this is in the red band. And you see that huge molecular band are seen in the spectra. For the carbon-rich stars, those are carbon molecules, and in the oxygen-rich, those are oxygen molecules like titanium oxide. And typically you see that the shape are different, and we use this shape actually to discriminate between oxygen and carbon-rich red giants in DR3. And as an example, this is showing a distribution of stars in the Magellanic Clouds. Those are all long period variables, and without going in the details, basically, these are carbon-rich and oxygen-rich stars. And if we apply our technique that we want to use for DR3, we can distinguish between these two very nicely. Okay, now a few words. This was about the tables that were published in specific variability catalog. But of course, we have the full Gaia archive, which is available. And one quantity that is published for every star which has a photometry is the uncertainty on the photometry in G, on the flux in G. And this uncertainty actually includes in its data the noise of the data, but also the variability of the star itself. And using this, we can use this quantity to estimate amplitude proxy, which typically is related to the range in the time series, the light curve, with a simple factor of 3.3. And the same thing can be done for the BP and the RP. As a function of the magnitude here, from 2 to 18, this is the amplitude proxy, and you see here very well the locus of constant stars, and everything which is above would be variable candidates. And these ones above this limit, which will be about 0.2 magnitude, are large amplitude variables. In DR2, there are 20 3 million candidates for these stars. And beautifully, on the HR diagram, the amplitude proxy distribution in the HR diagram is shown here, where the red are the largest amplitudes, and you recognize here long period variables. Our Lyrae are here, Cepheids are here, eclipsing binaries are there, and you can easily find other types of variables. If you do the same thing with the ratio of the amplitude proxies, which comes here, you have the ratio of the blue to red, and this gives an idea of the type of variability that you have, where you have eclipsing binaries which have a ratio wavelength non-dependent, which is around 1, but you have long period variables which are much more variable in the red than in the blue. And the same thing for Cepheids and our Lyrae, where you see it's about 1.6, and cataclysmic variables are here, and so on. So I want to finish now. I had one more example to show, but I will just mention it very briefly. It's a work done by Eliana Abrahams, a PhD student, which uses this amplitude proxy to identify cataclysmic variables in the full archive. Make some cross matches with the SIMBAT to see that a good recovery can be found. And typical among the 3,000 short period candidates found in DR2 with the amplitude proxy, 21 have light curves in the DR2, and you see them here, and 51 have light curves in the Gaia Alerts, which are here. And I will finish with the conclusions, showing that Gaia is really a wonderful mission for variability studies. 7-10 million variables are expected in DR3 in specific catalogs. And this is a summary of the number of CCD measurements so far recorded this morning by Gaia for the different CCD instruments. Thank you.
Excellent. Thank you, Nami. We might find some time for a very brief question, if there is any. Simon, yes.
Many thanks, Nami, for that. I'm curious about your variable white dwarf stars that are not on the CV sequence, but seem to be on the white dwarf sequence, and what might be happening with those.
Yeah, that's a. Let me see if I can find them back. Do you still see the screen?
Yes, we do.
Okay. So you are talking about these ones.
Exactly.
Yes, it's a good question actually, especially that these are large amplitude ones with amplitudes above 0.2 magnitudes. So this would require further investigation indeed. And as you can see, the ratio between the blue and the red is either non-existent or typical of kind of pulsating stars. But I do not exclude some maybe contamination from here.
Thank you.
Okay, thank you, Nami. I'm afraid we have to move on, but there is still chat. People can use chat to continue discussion, or you can use WonderMe in the break or afterwards. So thank you, Nami. We now move to William Tulloh, who's going to tell us about another unit of Gaia. William, please.
Okay. Looking for my presentation. Do you see my screen?
Yes, we do.
Okay. Well, I will give information on about the activity related to the asteroids, and in particular the new, potentially new asteroids detected by Gaia. For this activity, we have three groups of persons. The first group is the core team of the activity, but we have also people from the DEPAC Coordination Unit 4, related to the SSO, Solar System Object, and also many collaborators from outside, which are observers mainly from different countries. And all these people allow us to deal with the detection of potentially new asteroids by Gaia. As you know, we already publish for 14,000 asteroids in the data release 2. So they are known asteroids, and there will be more in the 2022. But we have also a continuous access possible for the data related to new asteroids, which are published through the Gaia Alert almost every day. And they are publicly available, and they need follow-up observation from the ground for the recovery. And this is the processing of these data, which are the short-term processing for alerts. And this scheme gives you the explanation of this process. We have the Gaia observations, which are treated by some step for identification. And if we have the detection of a non-cataloged asteroid, we have the computation of many preliminary orbits which are necessary to build alerts, and I will give you more detail later, which are publicly published and used in network to provide new observations to the center, the Minor Planet Center, which will also another center to build a database for asteroids, which is the ASTORB database. And this ASTORB database is the reference catalog to identify the asteroids observed by Gaia. So this is a loop, and by making this follow-up of alerts, we are able to feeding the ASTORB database and to allow Gaia in the future to identify these asteroids and avoid to send another alert for these objects. So this is the main goal of the activity relative to this new moving object. And we have built, in fact, a server in order to allow the observer to access his data. And this server is accessible at this address. And what is a challenge for the observer is to recover the asteroids from the ground, taking into account that we have a high parallax effect, and also that when we have the observations by Gaia, we have only a very short arc of orbit in order to build a preliminary orbit. So the method we use is to make a bundle of thousands orbits and to project these orbits on the sky, in fact, in order to give a kind of ephemerides and sky maps to the people in order to find the asteroids. And that means that we only are able to give a zone of probable presence of these asteroids, and they people, observers, have to use their field of view to pave eventually the zone in order to recover the asteroids. Well, we prepared the people long ago. We had 3 workshops in order to make the observer sensitive to this activity, but the alerts began really to be triggered at the end of 2016. And we saw that starting at this date, that the magnitude of the potentially new objects are in fact around 2021. So that means that only a telescope, say around 1 meter diameter, can observe this kind of alerts from the ground. On this figure, we have, in fact, the histogram of the magnitude for the ground-based in blue, and also on of the alerts that have been triggered. That we see that you cannot get some detection by amateur astronomer with small telescopes. Well, on the page of our server, we give the information under this form with the general information on the alerts, the sky map where we have to find the object, and also a kind of ephemerides here with the coordinate on the sky, and also the magnitude and the orientation of the velocity. We had several stations used, regularly used, in particular in Haute-Provence Observatory with a 1.2 meter telescope at the south of France, where we are able to make CCD classical observations, and we use that every 2 months. We also use a telescope at the south of France in Calais station with a remote telescope of 1 meter, and also there we had observations, but we in particular had the possibility to observe through the LCOGT, the Largescale global network of 1 meter robotic telescopes. And this was a very important step in this activity, because we got many asteroids with that kind of network very well adapted for observations on Alert. And we had also several observations from people, in particular in Ukraine, in Kiev, in Odessa, Terskol, and Abastumani. In total, these are the results we obtained at the end of last year. We catched 2,050 objects detected on Alert. And we saw, after sending them to Minor Planet Center, that most of the objects, in fact, were in the archive of the Minor Planet Center, awaiting for more precise observation to be in the ASTOR database. So almost 200 of these objects have been assigned by designation by Minor Planet Center. And this is one important result of the activity, which give, in fact, the possibility of this asteroid to be known thanks to the retrieving of these asteroids from the ground and very precise observations by Gaia. And only 6 objects were assigned to Gaia as discovered. But, well, we have this kind of number of detection by the colleagues from these observatories. And you see that the global network, Largescale, is very efficient because we got more than 100 asteroids. And
William lost 2 minutes.
Yes, okay, it's really good. And in fact, probably the most important result is this one. Among the 2,000 assignation given by Minor Planet Center, we got each orbital elements, and we are able to see the comparison of these elements with the elements of the well-known asteroids by Astorb in this normalized histogram. And we have that kind of situation for the semi-major axis. In gray, you have the Astorb situation. In the blue, the results for the activity of Gaia follow-up. And for eccentricity, we have this one with bias for the high eccentricity. And for the inclination, here we have a very visible bias for the high inclination. And that means that the activity of the detection of the Gaia alerts show that population of the main belt asteroids, the outer main belt, in fact, with high inclination are not well known, and this activity allows to enhance our knowledge of the main belt. Well, this is a summary. We worked on this activity since the end of 2016, and we showed that the short-term activity, short-term processing works well. We got a certain number of detection. We probably could not get more because the asteroids in this magnitude range are in fact relatively well known, but we show that for the high inclination and the outer main belt, our knowledge, actual knowledge, is poor, and we have been able to improve that. And all these results with much more detail are in publication, and actually it's only on arXiv, and it's submitted to the Astronomy and Astrophysics journal. So here you will be able to get more details. Finished.
Okay, thank you, William. We can have one question or comment quite quickly while we switch slides to the next speaker. Dirk, if you could switch slides, and we can have one quick question. There is a question on chat which we can quickly answer. Przemek Mróz asks, can Gaia detect asteroids whose orbits are entirely confined within Earth-Venus orbit?
Normally, for the asteroids in the Earth orbit, yes, it's possible, but we did not detect that. And in the Venus orbit, I'm not sure, because it's very close to the sun.
Okay, thank you, William. We can continue the discussion in the chat, and now we move on. It's Dirk Frebrich is going to tell us about how is citizen science. And Dirk, I will give you a warning after 10 minutes, okay?
Yeah, okay, thank you. You can all hear me? Yeah.
Yes.
Okay, thank you very much. I'm gonna give a short presentation about our Hunting Outbursting Young Stars citizen science project, which, as you can all guess, is investigating young stars. But we'll do this with amateur astronomers. So the idea is the amateur astronomers deliver the data and we are doing the science. What we do is we look at things like this, because they're pretty. This kind of, the idea is to motivate the amateurs to actually take pictures. And every amateur with a camera will probably have taken a picture of more or less all of these targets at some stage. What we are after is basically the images to look at the light curves of all the young stars in those regions. All the regions are selected to be closer than a kiloparsec. So things like solar luminosity object is 15th magnitude. This is what most of the amateur equipment can do, and most of the pictures that we have a limiting magnitude between 16 and 18. So we get very nice data or a high accuracy photometry for these brighter objects down to about 16 or 18 magnitudes. And as I said, they're all close by. The aim of the project is really to do high cadence. So one picture every 12 hours, monitoring of all our targets. And we want to do this in all the optical filters, so UV, RI, and hydrogen alpha. So we're still a bit away from actually having that target, but we are making progress. So we've now established a network of observatories spread over 11 countries with about, I think it's 76 people who send in data. There are a couple of professional telescopes in the network and some university ones, but most of the telescopes are amateur astronomers. We've made quite a huge number of brightness measurements. And what we do is we measure the brightness of all the stars in every single picture, and we keep them. And we use this to really accurately calibrate the photometry internally, including the color terms that you will get from some of the data which comes in slightly different filters, where the DSLR cameras, they have different filters depending on which one you buy. And that allows us to basically calibrate our data. Typically, the median error of the photometry is about 3 or 4% for a 15th magnitude star. What that allows us as well is basically every Gaia follow-up that shows up in one of our fields, we don't just provide follow-up data, we also have data before the object did something that made it come up as an alert. And that's one of the science things we want to do in terms of the young stars. We originally set out to investigate outbursts. How often do you get outbursts, of what strength, what frequency, and how that changes with mass, and so forth. You kind of want to know what happens before the outburst. You always get a lot of data after a big outburst, but no one really knows what's going on just before it happened. But the data is also useful for a lot of other things. You can look at occultation events by disk material. If you take a picture every 12 hours, you can really go down in terms of resolving disk structures all the way down to the size of the central star. So a couple of % of an AU. We can look naturally at rotation periods, spots, because we got multi-filtered data. You can measure the temperatures and the sizes of these spots, and we're doing this over years, so you can look at the evolution of these spots. I can even see them move on the surface if they do so. So these are all things that we do. This just gives you an indication how the project progressed. So basically the blue line gives the cumulative number of stars, of images that we have. And you can see, we've all seen exponential graphs over the last year or so. We are doing quite well. So we're getting more and more participants that send in more and more data over time. As I pointed out, I'm going to show you some examples now of objects. Basically, every star that is in the same picture as these alerts is going to have the same number of observations, because we keep all the data. And you never know what's going to happen to one of the stars nearby. And this was, as far as I'm aware, the first Gaia alert in one of our fields. a known variable star which had an FORI eruption in the early 1970s. I think I actually realized that the object went down before the Gaia Alert came out by looking at our data. And I was very excited because I thought, oh, great, maybe this is an FORI that finally goes back down to its original state. But it just turned out to be a dip. So there's probably something, a structure in the disk a little bit further out that occulted the star. And then it went back to kind of being normally boring and not doing a lot. But one thing to point out, all that scatter that you can see in the data, this is not noise in photometry. This is real scatter. So there are fluctuations probably of the accretion rate and the actual extinction over time. So we're going to use this to really study the structure of that material in great detail. So the second object, this is an object that every survey that makes alerts will pick up. So that basically Gaia has picked it up. The Palomar Transient Factory has picked it up at a different time. So it has a lot of numbers. And it's one of those very, very strange YSOs that goes up and down. You can see that in Gaia by 8 magnitudes at the very least over the course of a couple of years. You can see there's already a lot of structure in Gaia here, and our higher cadence data, you can see there's much more going on. In particular, the colors are very interesting. So there's no one-to-one correlation of brightness with color of this object. So there's a combination of accretion rate changes and occultation going on at the same time in that object. And no one really knows what's going on. There's been a lot of papers written about it, but again, that one just nicely shows what our data can do. And you can see that if you lose stuff at about 18 magnitude, then we can't see it in our data anymore. This was an actual FORI burst that Gaia picked up, and then we started following this up after it got detected, so round about here. In collaboration with Lynn Hillenbrand in the US. So that's why our light curve starts a bit later. That's one of the targets we just added to our list. We all panicked a bit when 2 years after we wrote the paper saying this is an FORI star, it started to dim again. But again, this is just one of those dips where probably something in the disk moves in front of the star. So that has all recovered. And last year, the star was well behaved for an FORI star, and hopefully will be for quite some time. Here are just some of the spectra. So I got that slide from Lynn. One of the interesting things is if you look at the light curve in the mid-infrared, what you can actually see, the outburst in the mid-infrared starts before you can detect any changes in the optical wavelengths. So that kind of puts some hints on how these objects actually evolve in the early stages, when typically we pick them up in the optical. But typically we don't have these information in the mid-infrared. So the last object, or the last two I want to show you is quite a nice way of seeing how these Gaia alerts work. This is one light curve of what we think is a Herbig AEB star that shows kind of regular eruptions, and Gaia never picked this up. So we know there's another eruption happening around here. So I think the pipeline basically says, oh, this is all variable, and never actually flags it up. So what we have, what you can basically do with these, with our data and some spectra. So this is the hydrogen alpha line at different times. So you clearly see there's a emission coming from the disk at quite high velocities. So we're talking 150 kilometers a second velocities for the two peaks here. So we can actually model, and I asked a student to do this. We simply model these outbreaks over time by simply a black body as a first example. And what you see is they all start at a high temperature, then cool down, while the kind of size of the black body kind of increases all the way to the peak typically, and then while the temperature stays constant, the kind of area of that emitting object kind of disappears. And all these peaks, the second peak behaves in a similar way. You have a high initial temperature, still way below the temperature of the star, of course. That drops all the way to roughly the maximum, which corresponds to this time here, and then roughly stays constant. So we had this object for a while, tried to figure out what that really was, because none of us knew about BE stars really in detail. And I found this light curve in one of the alerts, and I thought, oh, that looks exactly like the one that we have, with the only difference is that the peaks seem to get higher over time, and that's why Gaia picked it up compared to the one that we already have. But this object was in the south, so we have a nice member of our amateur group, Josh Hamsh, who's actually in the talk, I think, who provides this data where we caught the end of the first outburst after it got flagged up, and now almost the full second outburst. And we've done exactly the same. You can model these and you find exactly the same behavior. So that's another of these Herbig AB stars with more or less regular eruptions. So what you can basically do is, if you multiply temperature to the fourth times the area here, you get the accretion luminosity that's causing the light. And hence that gives you the mass accretion rate. And we can basically, with that really nice data from Josh here, we can basically day on day follow the mass accretion rate onto that object. That makes it very interesting. So that's basically all the examples. Thank you very much.
Thank you very much, Dirk. Very exciting stuff. I'm very much impressed by the quality of your light curves. We should definitely combine the data we collect for some, and then also have, well, maybe you could observe some of other types of events. Are there any quick questions to Dirk now? Anyone, please raise your hand or write the question in the chat. I don't see any, but as I said, I'm very pleased that you are actually observing those BE stars, because we find them plenty and we don't know what to do with them. So, and we're not interested scientifically, and they are crazy contaminants for us. So excellent, thank you. Let's move on. We might catch some time. We're already behind the schedule. The next talk will be the short poster talk by Malhar Kendurkar about data analysis and search for astronomical transients. Malhar, are you there?
Yes, I am. Can you hear me?
Yes, and we can see your slides.
Okay,
please.
Thank you. Hello all. I'm Malhar Kendurkar. I'm an undergraduate student here in Prince George, Canada, and I'm a president of Prince George Astronomical Observatory and principal investigator of Global Supernova Search Team. I'm going to talk about data analysis and search for astronomical transients. So about Global Supernova Search Team, I initially started this team back in 2018, August. And the goal of the team is to search for supernovas and take follow-up images of other sky surveys and to observe microlensing events, optical flares of quasars. So here we can see our main telescope, which is located in Prince George. So it has a wide field survey camera mounted on 0.6 meter telescope, and it is a part of GSMHD Survey. So we observe northern sky up to 2 times each night, depending on weather. And using this telescope, we have discovered around 17 supernovas and 3 novas in Andromeda Galaxy since 2018. And limiting magnitude of this telescope is 21 magnitude in 60-second exposure. And other telescope we have for GSMHD survey, one telescope is in northern Spain, which is a remote telescope, and in southwest France. And we also use SLU observatories, which is in Chile and in Spain. Some information about our survey telescopes. Prince George telescope is a 24-inch, which has a SBIG ST10 camera, and ST9 camera is on our spectrograph, which is We are still building our spectrograph. It will be ready by next year. And on Canary Islands and in Chile, SLU observatories, they have the same equipment, which is a 17-inch plane wave CDK telescope and a FLI Proline 16803 camera. And in Southwest France, we have a 10-inch telescope and a 12-inch, which uses Canon 1200D and QHY 183. So our discoveries overview since 2018 to 2020. So in 2018, we discovered around just only 3 supernovas in a whole year and found 35 false positive or iffy candidates. And in 2019, we found 10 supernovas and 47 false, around 40 false positive. And in 2020, we discovered 94 supernovas and 136 false positive, which are not reported anywhere. And these are some of the discoveries we made in 2020. That's a supernova type 1A and supernova type 2 and optical flare of quasars. So we also study variable stars, eclipsing binary stars. So this is a light curve of CY sig, an eclipsing binary star, which is, we study these variable stars in Northern Hemisphere, mostly using our 24-inch telescope in Prince George, and do the luminosity ratio errors with the star, with a mass. And the second one is one of the discovery of Delta Scuti candidate star out of 122 discoveries. So with the Delta Scuti type star has a period of 0.029. And we have discovered over 122 variable stars, and we still have to publish all those results. So GSMHD future plan, we are planning to set up 6 robotic telescopes in Northern British Columbia. Out of 6, 1 robotic telescope will be a rapid response telescope, which will observe our discoveries, possible candidates. So summary, our archival data of global supernova team will be publicly available from both the Northern and the Southern Hemisphere. And the data will be useful for study of variable stars, including times of minima, O-C curve, and radial velocities. We also monitor alerts from Gaia, ZTF, Atlas, and Assassin and in CV bands. And yeah, that's it. Thank you.
Okay, thank you, Malhar. I will suggest that we now switch to another, while Kasia is installing her slides. I have a quick question, maybe, unless there is someone else who wants to ask a very quick question. Nada, yeah, please.
Hi, yes, I have a question regarding those, regarding the criteria that you have for transient. So, because you mentioned that you have quite a lot of false positives. So yeah. How do you distinguish, I mean, what's your criteria to define something as a transient as candidate supernova?
Okay, so we take at least 3 observations of supernova candidates, and when we observe the first time, and we have our data sets, and we put all the data in our spreadsheet where we write all the candidates' name and including the magnitude and how many epochs the candidate is actually visible. So if a candidate, or if it's a false positive, it won't be visible in the next epoch. So when it's not visible in the next epoch, we put that in a false positive and we don't report it to TNS. So we usually report all our transient to TNS with at least 3 epochs.
So all those that are reported to the TNS are supposed to be, are supposed to be visible on all the frames?
All the epochs, yes, absolutely, okay. Yes. And at least three observations on 3 different days.
Mm-hmm. Okay, thank you.
Yeah, thank you.
Okay, thank you. I will have some questions and comment later on, maybe. We should definitely chat about some connections here, but I suggest now we move on. Thank you, Malhar. And now we move to the next couple of slides, talks will actually be about our favorite topic, which is microlensing. And Katarzyna Kruszyńska will do a great introduction to microlensing with Gaia. Kasia, please.
Okay, so first of all, can you see my slides?
Yes, we do.
Okay, great. Because I'm still confused how it works. Hello everyone, my name is Katarzyna Kruszyńska and I would like to present you today the highlights of microlensing events found in Gaia Science Alerts. So first of all, since I'm probably, I think I am probably the first person who is presenting on the topic of microlensing, I would like to introduce people who have no idea what that is. Essentially, gravitational microlensing occurs when a massive object passes in front of a background star, and the gravitational field of this massive object acts like a lens and causes brightening of the source star. So essentially, it works the same as gravitational lensing. However, because both the source and the lens belong to our galaxy or are very nearby, we cannot really see the deformed image of the source star unless we are using VLTI. But we can see everything happens quickly enough that we can actually see the change of brightness, which is great because we can detect it. Since the lens doesn't have to emit any light, this method can be used to detect dark objects such as planets or dark remnants of stellar evolution such as white dwarfs, neutron stars, or black holes. If you have a lot of events, you can also use microlensing events. You can also use this to analyze structure of the Milky Way using measuring optical depth, and this has been done, for example, by Przemek Mroz for Ogle survey. Microlensing has two parts. First one is photometric, which I had described. That, as you can see on the left-hand side, that when you have a lens, the lens is static and the source is moving. When the source is approaching the lens, you can see the change of brightness. However, because the deformation of an image appears, it means that also the position of the stars will shift, because now you don't have a single source, single point moving along some kind of trajectory. Now you have two images. And both of them have different brightness. One is brighter and the other one is less bright, which means that the center rate of light is going to shift, and this means that the position of light is going to shift. So this introduces another astrometric effect apart from parallax and other ones which are observed by Gaia, and this will also affect the measurement of parallax, which is present in Gaia data releases. And that's why Gaia is important for microlensing. So even though Gaia has very low cadence compared to other microlensing surveys, such as Ogle or MOA or others, so on average, each source is observed once every 30 days. And in the bulge, where most of the microlensing events occur, the cadence is even lower. It's absolutely horrible for microlensing. However, first thing is that Gaia is observing entire sky, which means it's observing the entire Milky Way. And secondly, because of that observable microlensing, because Gaia is an astrometric mission and eventually, the dog is moving, eventually will provide astrometric time series for sources which are bright enough, we will be able to detect astrometric microlensing on unprecedented scale. So far, it has been done only for a few sources, like single sources using HST, for example. But using Gaia time series, you will be able to see it for multiple microlensing candidates. And now I would like to present a little history of Gaia microlensing in Gaia Science Alerts. So when I first joined the project in 2017, we only had a handful of events. However, this changed quickly during the years. And by 2019, we had around 260 events, which was quite shocking for me. And this is the image from January, from basically from yesterday. Right now we are at 292 events, so that's still a lot. However, it's not such a huge change comparing to the almost 260 events from November 2019. This is because our sample has been very contaminated, and thanks to work of Paweł Zieliński and Ilknur Gezer and other collaborators, we have been able to weed out most of the contaminants, which are BE stars, YSOs, and AGB stars. However, the influx of the new how the detection of new events has been better is more visible on such histogram, which I like to present sometimes. Here on the y-axis there is the amount of events published, and here we have time separated in half years. So the first change that you can see is in second half of 2018, where I couldn't really understand, and then Łukasz explained to me that Gaia has observed the entire Milky Way enough times that we have gathered enough points in the baseline that it's much easier to detect new events. And second huge change was in the middle of 2019, where a new detector has been introduced into Gaia Science Alerts pipeline. This detector is called Skew von Neumann, and it is very sensitive to events which have a very slow gradual change in brightness. With that detector, we detect a lot of very weird quasars or BE stars, which are very often not published. But we also detect a lot of microlensing events, and that is really great. These are some highlights that we managed to gather along the years. I have chosen events for which we have nice follow-up. Most of the follow-up comes from events which have been observed by telescopes from OPTICON network. So thank you very much for your data. Along with other collaborators such as Lithuanian team Lithuanian team from Vilnius University, as well as LCO, and in the past we have also used REM telescope and SMARTS. The latest highlight that we have found is Gaia 20 FNR, which occurs towards Galactica Intercenter, so that's really exciting. And according to a model by Chris Rybicki, it might be a long event, but we still don't know. So that might be very interesting. And speaking of long events, Gaia has also detected many of those. Some of them are presented here. It's still unclear for some of them whether or not they are binary events or parallax events. So a parallax event occurs when the microlensing event is long enough that we have to include movement of the Earth in it. And my favorite one is Gaia 18 CBF, which was detected in 2018. However, it has, as you can see on the lower panel, it has started much earlier, and it's an extremely long event. And via modeling, we have found out that there are two solutions. Both of them have timescales of around 500 days. And 70 to 80% of light is coming from the source. Additionally, photometric analysis of archival data done by Marius Maskoliūnas from Vilnius University shows that this source, the source star, is probably located at from 14 to 23 kiloparsecs, which is very far. And this event is actually at -8, the B is -8 degrees. So it's actually going through the disk, and the source is probably in the galactic halo, which is very exciting. And using this information along with the data we have obtained via MCMC modeling of this event, we conclude, which is shown on the right-hand side on two panels, we conclude that the source is most likely, the lens is most likely a remnant, a dark remnant. I'm not sure what it is. located at around 6 kiloparsecs and of a mass of around 1 solar mass. So it might be a neutron star, I think, or probably a neutron star. And with that, I would like to end and show you the summary of my talk. So first of all, Gaia Science Alerts is publishing a lot of events from entire Milky Way, which is really exciting. And at some point, we will have sub-millimeter astrometry for each alert. And for events bright enough, we will be able to detect astrometric microlensing. And I would like to thank all of the collaborators again for their wonderful follow-up. And that's it. Thank you very much.
Okay, thank you, Kasia. Are there questions? Simon.
Hi, thanks for that. My question is this. The 300 and ever-raising number of microlensing events that you showed us, are they what you classify as candidates, or are those the confirmed ones in your statistics?
Well, all of the confirmed ones, which have been confirmed via spectroscopy by Pavel or Ilknor or others, they usually have published ATELs, and then it goes into Marshall, and then it's classified as 100% microlensing. Some of the events are still candidates and it's pending. Some of them we know they are microlensing based on the light curve, even even the patchy Gaia light curve in Gaia, but I think they could be 100% microlensing events. Whether or not they are in Marshall, that's a different question.
No, the reason I ask is you showed large numbers on your curve.
Yeah.
And 300 microlensing events was the number you said.
Yeah.
But if I understood Ilkner's presentation, then roughly a third or a little over the third of them are microlensing events.
Yeah.
So the number of microlensing events would be more like 100 from Gaia.
Yes. So actually from those, for example, for 2018, I think we got rid of all of the contaminants, as far as I remember, unlike previous years. 2019, some of the latest events are still pending. 2019, most of the events I have removed. And in 2020, there's still a lot of events which for which the light curve is unfolding, and we are not yet sure what that is. So
Okay.
the numbers will change, but
Sure.
Yeah.
Thank you. Thanks for that.
Yeah, no problem.
Any more questions to Katarzyna? I will just use the opportunity of the chairperson, and I will correct the slide we see now. It's not sub-millimeter astrometry, but it's sub-milli arcsecond. It's an important point,
sorry.
but it's okay. But just to be clear,
Yeah.
that we're not talking about sub-millimeter observations.
Yes,
That would be
obviously.
great to get sub-millimeter astrometry as well, but not this kind of sources. Marcus,
I will
a
stop
question, and we will switch slides to Chris in the meantime.
I think thanks very much for that remark, and thanks very much, Katja, for that nice talk. The quick question is, how many events will have a astrometric signature so that you can actually get an astrometric curve out of the 300 that you've shown?
As far as I remember, most of the events that we have are not bright enough. Most of them have baseline of around 19 magnitudes or 18 magnitudes. And the microlensing astrometric shift can be observed for microlensing event with a baseline magnitude of 15.5 or something along the lines. Chris can correct me. I haven't counted how much of them are that, but that would probably be, I don't know, maybe 30% or less of the events that we are detecting.
Less. The answer is few.
Oh, yeah. However, like I remember your results that for events which are massive enough, there will be an astrometric shift, right?
Yes, yes, yes. So if they are massive enough, then can be fainter, but generally I suspect that it will be few events with astrometric signatures.
Okay, and in that way, we just gave voice to our next speaker, which is Chris Rybicki, who's going to tell us about maybe not astrometric microlensing this time, but about Gaia 19 BLD. Chris, please.
Yes, thank you. So after this great introduction by Kasia, I will just focus on one particular event, which is Gaia 19 BLD. and it's very special in many different ways. So let me move the camera. So in general, in microlensing for the standard events, so as you will see here, the standard events are not very useful in terms of determining the physical parameters, because as you can see at the bottom, the magnification of the event, I'm sorry, magnification of the event basically depends on three parameters, and only one of them, the Einstein timescale, is related to physical parameters of the lens and the source. So to search for, to look for example, lens masses or distances, we need to find other effects, some special signatures in the light curve. So, for example, the parallax can be helpful. The caustic crossings in either binary events or high magnification single lens events. Generally, the more features we have, the more parameters we can determine. So without going into details of microlensing, I just want to mention this equation. Because generally this is what we are after, the mass of the lens, because the objects we are most interested in are hopefully stellar mass black holes, but generally objects that are invisible and can't really be measured and weighted in any other way. But to get this mass, we need both of these parameters, theta e, which is the angular scale of the microlensing event, the Einstein radius, and the parallax. This pi e parameter is proportional to the parallax signal visible in the light curve. So both of them are relatively hard to get, but for this particular event, I will talk about. We measured them both. Actually, we measured them in many different ways, so we have it pretty well determined. So for the event itself, it was a great example of how we would like every microlensing event we are after in Gaia Science Alerts, how it should be, because it was very bright, so convenient to follow up. It was on Southern Hemisphere, which gave us access to network of robotic telescopes and quick response. It was alerted early as well, so we could cover the whole light curve. And it was also in oval fields, so we did have access to historic magnitudes so that we could tell more about or be more sure about the microlensing nature of the event. So the thing that stands out the most in this particular event is the shape of the light curve. So it's not, we do have some, this additional feature I've been talking before. And in this case, we have the, look at the middle panel where the red dot is a lens and the open circle is a source. So in this case, we not only have very close, very close passage of the source of the projected separation in the lens, but we actually have lens transiting in front of the source disk. And because of that, when the source is in front of the very disk of the star, the lens is in front of the very disk of the source, we do have, instead of two images that are normally produced, we have the complete Einstein ring. And most importantly, this feature is visible in the light curve. So you see that by measuring properly covering the light curve, we actually can indirectly measure theta e, because the size of this ring is theta e that is needed to determine the mass of the lens. So okay, let me put it from the beginning to the end. And so this is the event itself, the light curve with real data. Now here, before I go to the more detailed areas that I marked here with boxes, let me just emphasize one important thing. So you see these red diamonds are Gaia measurements and Gaia observations. And other points are basically follow-up. We do also have survey data from OGLE, but only survey data from both OGLE and Gaia are not enough to accurately determine all the parameters that we are after. So you see that the coverage is very dense thanks to our follow-up, and that's why we were able to investigate this event quite thoroughly. So this is the close-up. You see that the peak of the event is covered pretty well. There are some systematics you see here, for example, but it's probably due to moon influence, which was in full phase during the peak. But still, it was enough to measure all the things that we actually wanted to measure. And the red light curve here is how the event look like from perspective of Gaia. So as you can see, from L2, the projected separation of source and lens looks or changes in time a little bit differently. And yeah, the size of this hat, this flattening in the light curve peak is proportional to, well, the thing we get from the light curve is angular size of the source in the units of theta e. So if you have angular size of the source in milliarc seconds or whatever unit, you can actually derive the theta e. So we already have the photometric follow-up, the ground-based survey photometry, the photometry from 2 satellites, but we actually wanted or needed really more information about this event. So to gather all the necessary information about the source, we also did the spectroscopic follow-up of the event with both high resolution and low resolution spectrographs. And thanks to some modeling, we were able to derive the basic parameter like temperature and metallicity, gravity, surface gravity of the object, of the source. And along with the measuring of extinction, we were able to derive distance to the source for approximately 8.4 kiloparsecs. But let me just remind you that this is a disk event, so this is not toward the bulge. So this distance is just coincidentally close to distance to the bulge. And the last thing I wanted to mention is that thanks to the fact that the event was extremely bright, we can actually hope to, what is related to question of Marcus, we hope to actually see the astrometric microlensing deviation in the last data releases of Gaia. So we do need the astrometric time series to be able to tell anything about this. Actually, for the event was so bright that for few epochs, I think effectively for 2 epochs, it will be possible. The 2D Gaia astrometry will be available because for 2 epochs, it was brighter than 13 magnitudes in G. So yeah, so this is my graphical summary of what we have actually done. So our goal was to measure the mass of the lens, and it is slightly above 1 solar masses. So we were able to use use follow-up to cover the peak of the event so that we could measure finite source effect, which allowed in turn to measure theta e. We measured parallax, both using Spitzer follow-up, the magenta curve I didn't mention, you see here. We also used ground-based data and light curve asymmetry to yet another determination of pi e parameter. We did use spectroscopic follow-up to determine all the parameters of the source. And it also will be possible, hopefully in the future, to measure theta E using Gaia astrometry and to detect by detecting astrometric microlensing deviation. And now the last, but definitely not least thing that we actually did was the follow-up observation using Pioneer instrument on VLTI, because the event was extremely bright, so the interferometric follow-up was possible here. And apart from measuring theta E, we measured a few other cool effects. So stay tuned for that. Well, 3 papers on this event are on the way. They are in the review process, so you should see the results pretty soon, hopefully. So these are conclusions. I think I'll leave you with them. Just let me emphasize that here in microlensing, we don't really care about the light from the lens. So it is perfectly viable to do all this I just described for example, star mass black holes. And also, as you also seen, it will not be possible without the very dense and precise follow-up from the ground. So keep your work going. I'll stop here. Thank you.
Okay, thank you, Chris. Are there any questions to Chris? I don't see any. So thank you, Chris. And let's stop here for 15 minutes. I remind people that there is still this Wonder Me room going on. And yesterday it was quite, and previous day it was nice to catch up with some of you and continue the discussions. There is also Slack channel I remind you about. Please join there, and we use it for exchange of information. So I'll stop me talking, and let's meet again at in a bit less than 15 minutes, so 13 minutes, 7:45 Polish time. And I'll keep this Zoom running, but feel free to take a break, make a coffee, or go to Wonder Room. Thank you. Okay, hello, hello. Welcome back. I hope everyone had a great break. I do recommend Wonder. We just had a nice conversation, and I almost missed this session. We can meet after this session as well. So, okay, without any further delays, there is Zosia Kaczmarek, who's going to tell us more about lensing events with parallax in Gaia Alert. Zosia, please.
Okay, can you hear me and see my slides?
Yes.
Okay, everything is fine. Great. So hello, everyone. My name is Zofia Kaczmarek. I am a master's student at the University of Warsaw, and I have been working for some time on lensing events in Łukasz's team. And lately, we have intensified our efforts to study lensing events with parallax, and I want to tell you about it today. So first, what are microlensing events with parallax? So Kasia has shown the basic principle of microlensing when the star that is the lens, the star that is the source, the massive object that is the lens, and us, the observer, are aligned in one line. However, in some events, there are changes in R, the observer's position, that are due to the orbit around the sun. And this causes wiggles that we can see in the light curve that occur with a period of 1 year, because that's the period of our movement on the orbit. And sometimes these effects are very, very subtle, and you can only see a slight asymmetry in the events. While sometimes, and in particular in long events, you can see multiple bumps in the light curve. So as you see, these events look very exotic, very interesting, but why do we study them? Parallax is very valuable if we can observe it and measure it, because it's a degeneracy breaker. Usually the only information tied to physical parameters that we have is the Einstein time. When we have parallax, we have more information about the mass of the lens, the distance to the lens, and basically the only thing that's missing is the information about the distance to the source and mu-rel, which is the relative movement of the source and the lens. So I won't go into details of the math and physics behind it. If you want more info about the method, you can check out the paper I'm citing here. But basically, we are looking into it because the parallax helps us determine the nature of the lens. How we are doing it, of course, it can't be done analytically, as there are too many different parameters that are all tied to each other in complicated ways. So we do MCMC modeling. So we let out random walkers to the parameter space, and we look if we can reproduce the light curve well. So this is what we get, some sort of Gaussian distributions of the values of the parameters. So as I said, we take the values of those parameters, so the parallax, the Einstein time, we take the distance to the source, which can be done, for example, for red clump stars, where we know how far they are. And we take the galactic bulge kinematics, which are very well defined. So this is how we've been doing it with ogle events. And it has been a great tool to determine masses and distances of the lens. Also, we were able, when we are able to tell the distance of the lens, the mass of the lens, we can say, okay, if it's a main sequence star of this mass located at this distance, it should give us this amount of light. And we could check whether we actually see it, whether we see this light blended with the light of the source. If yes, if it's consistent with these assumptions, it is a main sequence star. If not, it might be a remnant, a black hole, a neutron star. So that has been a great tool for ogle data, and what we are doing now is we are moving to the application to Gaia data. Why do we want to use Gaia data? Well, the answer is here on this map on the left that covers all Gaia alerts. With red, the events from the last 20 days are marked. So Gaia is scanning the entire sky in real time, and we really want this all sky coverage not to be limited to just one very well-known region. So this is a huge advantage. And also, as we have this real-time information, we have also this great network and collaboration that shows on this conference. We can also have some spectroscopic and photometric follow-up from our collaborators. So here I would like to really highlight it, because it is a problem for us when we are moving from high cadence observations to low cadence, to Gaia cadence observations. We really need follow-up to model most of those events. And here, as a positive motivation, I will show one event when the follow-up actually made it possible for us to pinpoint the peak of the event. So in Gaia data, there was this huge gap that only because of follow-up we were able to know how high is the peak and when it happens. Sorry, there's some distraction in the background. So I would like to motivate you to first do follow-up for us. Second, do follow-up for us even when the event is no more doing something interesting, when it's at the baseline, because it's those points about 9,000 years on the plot that help us level out different bands, because that's a problem with multi-band modeling, and we have to anchor it to some point. So even when events are not doing something interesting, please continue observing and continue following. Okay, so another problem is that Gaia finds those events all around the sky. We are pointing in very different directions, but here is where the service called Besson model of the galaxy is helpful, because we can basically submit any direction on the sky and retrieve a mock-up catalog of stellar populations and stellar kinematics in this direction. So as they are very pretty combined Gaussian distributions, it is actually really easy to fit them and to include them in the code. So our final routine now looks like that. We are using Besson model kinematics. We are using the models, which are more or less unchanged, except for that we are doing multi-band modeling. And we are using distance to the source. So we can have it, for example, from spectroscopy. Here, what might be puzzling is why we are not using Gaia, if, of course, Gaia is providing superb astrometry that we can use for parallaxes. But it is very important to note that, as Chris has said, microlensing not only influences the photometry, it also influences the astrometry. So Gaia can't really fit the right solution that is very simple, that is just proper motion plus parallax, to those weird anomalous paths on the sky. So until at least we have time series astrometry, we can do nothing with that. Anyway, with all those elements, we managed to make, we managed to develop a routine, and we are studying already the Gaia alerts. We are retrieving the mass of and the distance of the lens. And now I would like to show just very, very quickly, as I see I have 2 minutes left, some highlights. So I chose just those events that are ongoing and that can have some improvements to them, actually. So one is our lately favorite event, Gaia 19 DKE, that Marius will tell more about. I will just say that first, it's an ongoing event with strong parallax, and we were able to get really terrific follow-up on that from many, many bands, many observatories. And as you can see on the right, this great follow-up allowed us to really well constrain the model. So as for now, we can say that with a huge probability, it's a low mass star. It's a star that is a few times lighter than our sun, but it's still most probably a main sequence star. The code returns an 80% probability that it's a main sequence star. So perhaps we will have to wait some more time for our black hole. And the last event I would like to show is Gaia 20 CFP, which is an ongoing event with very, very strong parallax. And you can see that the changes are really dramatic, and also that there are more wiggles coming, and there will be more observations and efforts to constrain it. And what is interesting here is that the lens is actually very bright. It's responsible for for more than 90% of the light in this blended light curve, actually. And also it's very nearby. So our very tentative calculations say that it should be even less than 1 kiloparsec from us. So that will be really a great event, a very interesting event to study when we have more data in the future wiggles. So that's all. And I would like to thank you very much for your attention. And if you have any questions, I'll be happy to answer them.
Thank you very much, Zosia. Are there questions? Etienne, please.
Hello, very good talk. I wanted to know how you take account of the extinction for the magnitude estimation of your lens. Do you take it from the Besançon model or?
Okay, so it varies, and actually in the case of Gaia 19 DKE, I think we actually got extinction from the data from you. So I remember getting the extinction values from Pavel that were from you initially, but sometimes we are also using net extragalactic extinction calculator. So basically we can enter the coordinates and it returns the extinction in different bands. So it's not perfectly precise, but it's enough to have a reasonable values.
Okay, thank you.
Pavel?
Yes, I can comment this a little bit. Well, so the extinction was taken from the well-known Schlafly, Finkbeiner, and Schlegel models, but this is just as a first guess or preliminary value of extinction for this target. And I have a question to Zosia.
Okay.
What is VV and WW in Besançon model of the galaxy? Because I'm not familiar.
Okay, so basically the Besançon model returns a three-dimensional velocity in the galaxy. So we are interested just in those that are that we see like that are not radial but tangential to our line of view. So WW and VV are two components in the galactic spherical system for those velocities.
Mm-hmm. Okay.
So we just have the values of them for the lens, the values to the source. So those four values give us Murel in total.
I see. Okay, thanks.
Okay, thank you, Zosia.
Thank you.
Let's move on to Marius Maskulinas from Vilnius, who's going to tell us more details about Gaia 19 DKE. Marius, please.
Okay, hello. Do you see my first slide?
Yes, we do.
And mouse as well, yes?
Yes, as well. Mm-hmm.
Okay, thank you. So thank you, Zofia, it is, and thank you that it is the discussion I hear about extinction. So here it will be, in my presentation, will be more details about actual extinction. But it is, I would like to present you preliminary results for the microlensing event Gaia 19 DKE. Why preliminary? Because it is still ongoing event, not yet finished. So, but nevertheless, we can already some data show for you. So first of all, thanks for massive follow-up campaign allowed us to collect a very detailed light cover for Gaia 19 decay. And the Gaia 19 decay event was detected by Gaia satellite on 2019, 8th of August. And later to this event joined the network of ground-based telescope. So, and here it is, you see the page from the follow-up. So actually, Molėtų Observatory in Lithuania is one of the leader of this object because it is in the northern part of northern of sky. And here it is in the middle. You see the real image from the Molėtų Observatory, the made telescope. Actually, due to the not precise pointing, you see that with our source it is slightly moved to the right side of the image. It's typical situation, and as observers know it. So here I present the light follow-up, and it is data points from the different observatories. So thanks to the high brightness actually of this event, no, not exactly this event of source stars, it could easily follow up even with smaller telescopes which provide dense coverage from the ground. But it is we see in this diagram. So, and first observer who joined into this follow-up was Goran Demjanovic. I hope I correct say from Serbia, and I am not sure he is participating today, but yesterday I saw his name in the participation. So he joined it is 21 days after the alert was published. So thanks, Goran, you are a very lucky astronomer actually. First predicted where to point your telescope. And congratulations. Okay, so I quickly observed, or using this diagram, it is now 10 observatories with Gaia. Ground-based it is 9 observatories. So I would like to draw your attention. So if you did observation for this Gaia 19 decay object, let me know if you are not on this list, on this table. So, and second, what I would like to observe is to draw your attention that it is, please put attention to this point that I show you with mouse. Actually, these points are, let's say, not correct. Actually, if it is possible, could you fix this points? Because from my practices, I know that it is in the beginning to more than 2 years ago when we started this activity with follow up. So we also saw our points. It is on the not in line or not too closer to the line, but it is follow up go. So it can be a lot of reasons. So maybe it's extractor, maybe something. So I recommend for you that you already saw the presentation with new version of Black Hole Tom. So it is possible upload FITS file. So please fix it. Or try to fix it. I'm not talking what it is need to do now, today, or fast, because this event is still ongoing. So, but we still have a lot of time. But with this, some points that you see on the bottom of this diagram, it is something wrong actually. Okay, but now go to the preliminary results. So, as I mentioned, event not ended yet. It is in here I present the model from Chris Rybitsky that you hear his presentation few hours, not few hours after. maybe 1 hour ago. So now it is event, it is about right in this point. This peak is probably, if it's, you believe that it is probably, it is the right model. Yes, so this peak that it is by my mouse, it is shows you it should be about this year on April. And we expect that it is our light cover, our follow-up will follow this lines. So now it is for source star. The spectra was obtained, and we got the spectra that it was close on the peak of this. And the spectra was obtained by the Large Binocular Telescope. It is located on south of Arizona. And we got spectra, and for spectra we used instrument Pepsi, but this Pepsi has nothing to do with the foremost drink. It is simply the first letter of the Potsdam Inhale polarimetric and spectroscopic instrument. And it is spectral resolution, it is from 383 to 907 nanometers. So according to spectra, we got results. So effective temperature, log G, and metallicity. So actually we see that it is G5 giant metal-rich star from the spectra. It is with information that it is needed for us to know the source star. Now a little bit about Gaia data. Here it is already, this slide already you saw in one of the first presentations in Monday. So it is this is familiar for you. But here I would like to draw your attention in this bubble that it is parallax and proper motions. Is it reliable in our case? So okay, so this microlensing animation maybe not so good, but you already saw today it is from Katarzyna and from Chris maybe better animations. But the idea it is that it is during the microlensing event, maybe this parallaxes, measured parallaxes by Gaia are not reliable. And how it is in reality. So if you take data from the Gaia data release second, so it is, and we take only parallaxes, yes, measurements. So it is our source star located in approximately 7.6 kiloparsecs. Later, what early data released 3, but it is already 9.5 kiloparsecs. So probably this value, it is affected by microlensing more. So that it gives some bad measurements from parallax. So we apply for our method. It is based on spectrophotometric method. This is typically based on this distance model equations. So actually in this equation that you see, there are many inaccurate in this equation and difficulties to determine. And nowadays it is much debate about the reliability of this equation, if it is possible to use it in astronomy. I personally know a few astronomers who even don't want to hear or see this equation, but they say that it is the nonsense to use this equation. But if it's not our choice, so probably it is one of the way. So since we know the spectral and luminosity classes of our source star, preliminary no absolute magnitude, preliminary no magnitude on base light, extinction. Here it is taken extinction from the Schlegel. So it is 1.1 magnitude. So if you put these values to this equation, we got that it is distance about 6 kiloparsecs. Yes. Thanks to that it is source, it is bright. So we can apply and other data. So it is to mass all sky survey data. It is good tool for bright sources. It was published with data long before the Gaia, and our source star wasn't affected by any microlensing events at that time.
Marius, 2 minutes.
Oh, okay, thank you. So okay, so very basically, yes. Here it is this green point. It is data from 2MASS. It is our source star Gaia 19 DKE. Here it is its location. Yes. Here it is with red. It is giant sequence. It is blue. It is main sequence star. It is with spectral luminosity classes. So actually, if we take if you know that it is our G5 giant, so it is our intrinsic position, or not reddening star located where it is, where is my mouse. Yes. So it is with distance, it is reddening. Yes. And here it is. So if we put extinction calculation, yes. So we know that it is intrinsic position, that is for G5, it is here. So it is in K band in infrared, it is 0.221 magnitude. Actually, if we want to got extinction in V, as usually, so we should amplify by 8.5. It is well-known ratio. So if we're using this infrared data, so probably it is little bit too much extinction. But if we put to this equation, as well, so same equation like in the previous page, yes, put this with all parameters, yes. So we got distance 6.1 kiloparsec. It is like for photometry, it is unbelievable. It is very precise and good results, and it's confirmed our prediction where it is exactly this source exists. So preliminary results, what we know about our source star. It is G5 giant. We got it is with information from the spectra. It is extinction probably it is between 1.1, about maybe a little bit. Distance about 6 kiloparsecs. And where it is located in our galaxy. So from the sun, it is, since the galactic coordinate, it is 62 longitude. So where it is our source star? It is somewhere in between Perseus and Sagittarius. And since it is the spectral analysis provides us information that this is metal-rich star, or close to the rich, it is close to the solar. If we see to this position where it is located, our source star, so we see that it is to the center of our galaxy, it is closer than even our sun. So when we know, or when we keep in mind that it is the galaxy metallicity gradient, so probably it is explained why it is this star, it is metal rich. If you look, for example, if you found the star, it is where is my mouse in opposite side, yes. So probably it is not exactly, or maybe I'm not sure that it is on the same, but it is about metallicity. Now about lens mass. Due to the CRIS modeling, it is clear that the lens mass, it is less than 1 solar masses. It's actually less than 1 solar masses. It is good news and bad news. Good news because we approximately know that it is the small mass. Bad news it is, I think you understand from the second slide. Bad news it is because this work is a part of the research project Polish-Lithuanian Black Hole Hunt, and we try to find a single black hole, and unfortunately this event not promising to be black hole actually. So, and supported by grants from the Polish National Science Center and by Research Council of Lithuania. I particularly acknowledge Lukasz and other his team members, Pavel, Ignor, Mariusz, Katarzyna, Chris, Nada, Algita, and as well as my team, it is my colleagues and my students, Erika, Justas, Vytautas, Šepas, Kotryna, Rimas, Rūta. All, thank you very much for all observers of the event Gaia 19 DKA, and of course, European Space Mission Gaia. So thanks you very much for your attention. That's all what I wanted to say. I hope I in time, so.
Thank you, Marius. Thank you. We might have time for one question while the next speaker, Ashish, is installing his slides. Any questions to Marius? Okay, great. Let's thank you, Marius. And we move on. We have to move on. We can discuss it later at the chat, so we keep with time. So now we have Ashish Mahabal, who's connecting to us from the US, and that's why we have this meeting so late. I hope it's convenient for all the US people. And Ashish is going to tell us about ZTF, machine learning, and variability. Ashish, please.
Good morning, good afternoon, and good evening, wherever you are. My name is Ashish Mahabal. I am the lead for ZTF machine learning, and I'm at Caltech. And as Vukash just mentioned, I'm going to talk about ZTF ML, but mostly about variability. So this is the ZTF description. You all perhaps already know it, but just a couple salient points that it's a large camera, 47 square degrees in a single field. We go down to about 20.5 magnitudes. Typical observations are 30 seconds, and we cover about 20,000 square degrees every 3 nights or so in G and R, and less frequently in I. And this is the team of members, some of the leads that I show here. And of course, there are many, many others who do much of the real work who are not mentioned here, and some specific names I'll mention later who are involved in the variability project. So one thing that I would like to also quickly mention, that DR4 was recently released. And if you go to the DR4 page that I mentioned about, you can see the gory details about it. But a couple of points that will catch your eyes. If you look at the number on the bottom left, 295 billion. So that's the number of detections that are there in the psi sources for all the filters together and all sources. So clearly a huge data set, and it's out there to play. And we also have an API access to that, so you can pull various things out of that. These are the 3 sky coverages that are shown in the 3 filters, GR and I. So a lot of fun things that are possible with that. So in ML, we are doing lots and lots of things. On the left-hand side, you see that from the raw data, we start with difference imaging. And the first thing that we have to do is separate the real and bogus and look for transients in different ways. The transient is not a spelling mistake, but that's something that's been developing, where we have been trying to do direct image subtraction to get transients, and that's been progressing. So there was a recent one where, for instance, we were able to find comets using a very similar technique. So that's going on. But the left-hand side bottom thing that you see, catalogs and time series, that is one of the crucial things, because we are very much into real-time transients and real-time alerts and so on. But as time passes, the catalogs accrue, the time series accrue, and a lot of science that can be done with that. And for the transients, as shown on the right-hand side, that we look at extragalactic systems from the solar system, there are lots of things that are found and so on. So the main currency of the real-time part is this alert, where we have got 3 cutouts. There is the latest image, the reference image, and the subtraction image. And the light curve from the previous 30 days is provided with that. Now, forced photometry is also provided on ZTF data. So that's something that you can take advantage of that. And there are many metadata parameters that are available with the cutouts. But again, what I'm going to concentrate today on are variables from ZTF. And in the first talk today, Nami provided an excellent introduction to variability and how this diagram also got put together. So Iyer and Malawi and their group, they have been doing fantastic work, and entire Gaia team, in fact, doing on all this. So with ZTF, there are 100K alerts, and what we are interested in doing is understanding which of them are what classes. And as we get into rare classes, it's more important that we have a background or a big data set for many of them. And that has been a bottleneck for a long time, because there are certain classes for which we have lots of data and we understand them quite well, but for many others, not so much. And so we are trying to now combine the time series as well as features from the time series that we get to see how we can do all that. And again, the determination of rarity is crucial because observing the same type of objects again and again is not going to push our knowledge limits much. So one of the decisions that we did is that we'll do the classification not as a multi-class classifier, but as binary classifiers. So for every class that we are interested in, or even every umbrella class that we are interested in, for instance, variable, non-variable. So a variable will be a class in some sense. We do binary classification. So given an object, we ask this question about it for each of the classes. Is it variable or not? Before that, we ask bogus or not, because many of the classes that we get later on, sometimes because of odd 1 or 2 light curve points, they could be bogus, which are masquerading as a particular class. So real or bogus, and then variable or non-variable. And then within that, we have 2 different kinds of classifiers, phenomenological classification and ontological classification. And then of course, there'll be overlap between those 2. But by having these separate classifiers, what we can do is that we can bring together that information from phenomenological types and ontological types quite easily. And then what you see on the diagram on the bottom right, for each of class, we are essentially asking, is it X or not X, Y or not Y? And then we can combine them easily. So because otherwise what you normally find is that when people have concentrated on 2 specific classes, it's easy to separate between, say, type flaring and delta scooting. But then if a object comes in which is of neither of those 2 types, the classifier, it was trained only on those 2 types, it's not really easy to get into the third one. And by going into binary classification, we can get around that. So what we decided to do is we concentrated on 20 fields. This paper by Jan is with the referees right now, and it should be published very soon. We picked up these 20 fields, and we looked at all kinds of objects in those and did those, getting the periodicity from those, features from those, and so on. And a large number of people contributed to that. Dimitri Douay put together a fantastic interface, and Shremak is going to give the next talk. He has been involved in classifying objects to a great deal, and I mentioned the other names there, Michael Coughlin and Andrew Drake and Matthew Graham, Lynn Hillenbrand, and so on, and many other ZTF collaborators. So he brought these together and started doing these classifications. This is a paper that's already published by Michael Coughlin et al. So you see on the left-hand side how when you take different features for specific classes, and here I'm showing variable versus non-variable, the features can separate them. We use the same thing for all binary classifications. So for each classifier, for each feature, we can look at such a diagram, we meaning the machines look at it, of course, and then together using the mechanisms, the classifiers that we have put together, they can give it probabilities of different kinds. And I show on the right-hand side a few features that, that we use. There are more, of course, I have not included them here. These are standard ones that get used again and again. But using these, and for specific types of objects, we are starting to get into specific features that will be useful. And that is where the coverage comes into picture. That is where the dimensionality reduction comes into picture. So that is one of the focus areas that we have now. Here are a few examples of different periodic variables at different periods. You see that they go from short period ones to long period ones towards the end. And each of them has many, many categories. And then we show all 3 filters in these diagrams. And that's the other thing that you will notice, that many of them will have very few I-band points. And even G and R, there'll be different number of points that you will see in them. This is the interface that was put together to look at individual objects. So we would, initial classification would be done. We would pull objects of a given class, and then all the classifier buttons that you see below, those are the ones where we have 0 or 0.25 or 0.5, 0.75 and 1. So for each of them, you can do the slider bar. You can say that it almost certainly is a variable. But if you're not completely sure that it's a variable, you could put it 0.75, for instance. And that information then goes to the back end. And at the back end, then the machines can make use of that. So this active learning we found to be very useful. And a lot of metadata is available with this. You see that at the top right. So when one looks at it, one tries to take holistically into account the features that are available, the light curve that you can see. And of course, this is interactive. So what you can do is that you can use a different period if you wanted to, and then zoom in onto a given region to see whether a given point is resulting into some kind of misclassification and put it accordingly. And because we are giving these different classifications, and then each of these is going to become part of every binary classifier. So even if something gets classified as RR Lyrae, that goes into all the other classifiers, and it should come out of there as none of that type to be correctly classified as RR Lyrae. So there are interesting things that happen because of these binary classifications, and I'll come to that probability related thing a bit later. But this is the large scale flowchart that we have. We start with the ZTF light curves, of course, but other inputs that we do get are from Gaia and from pan-stars and from all wides, because those are crucial inputs as we try to figure out various details of the various characterizations of each source. And then we use two classifiers. There is a neural network and there is XGBoost. And so for neural network, we use feature vector, which comes from some of the things that I showed you, but also a DMDT. This is the diagram that we use, convert the light curve into a 2D image so that it can be used with a CNN. And that goes into the convolutional branch of it. And we get class probabilities from these. This is a t-SNE diagram showing on the left-hand side just the first classifier, the variable, non-variable. And then once you have taken out the non-variables from there, you separate it into various individual variable classes. And that is what you see on the right-hand side. So even among the variables or among the non-variables, there were hidden some of the different kinds of variables. And that is where what I was saying is that the probabilities that we get from these individual classifiers can be in contrast. So some things in the parameter space that are in the non-variable region, there could be hiding some specific types of variables. And of course, this is only a 2D space, so that's not very surprising because the real dimensionality is much larger. And if we were to see it in n-dimensional space, then that separation would be easy. But that's the whole point, that when you're looking at certain features, certain projections, then there can be overlaps that you're not aware of. And getting to that becomes important. And that is where this active learning really helps. So for phenomenological classes, for instance, these are the ones that we are using. And the diagram that is on the left, that is the kind that we build for each classifier then. That shows that a given object, what is its likelihood of being of each of these classes. And depending on then the grayscale, then you can be more or less confident about that particular classification. So this is XGBoost result, for instance, and I'm highlighting specifically the areas where the precision is smaller or the recall is smaller. And this is where, again, I want to highlight what I said earlier, that it depends a great deal on how big your training set is. So even if there are methods, XGBoost, for instance, even if the two sets are unbalanced, it can handle that. But when you say that it can handle that, what it means is that it's not really skewing your answers, but your answers do get affected in terms of the accuracy or precision that you get. And so some of the wrong answers are essentially because the data sets, the training sets for individual classes are not large. And that is where we are starting to increase them more and more. And of course, because these classes, the probabilities are derived independently, there is a lot of overlap that you can see sometimes in different classes. So that's again something we are focusing on, trying to understand the edge cases and getting better. And then when it comes to trying to reduce the dimensionality, there are some interesting things coming. This is with XGBoost, for instance. If I am using only the overlapping ways, then what is it that I'm going to get? Just give me a sec. I'm going to turn this off. Yeah. So if I use only the raw ones, you can see that which parameters are important. You can see that Stetson K is quite important, skew is quite important, as one would expect, or Stetson J also inverse 1:1 ratio. But if I bring in the phased features where we have already fitted the light curve, found the period, and then use the phased ones from them, then suddenly some of the phased ones are seen to be more important. The a relative phi1 or the F1 power. Stetson J is still important, of course, but you can see that there are 4 or 5. And then if we bring in the external ones like the Gaia DR2 photometry, PPRP excess factors, that is seen to be important. And the period is seen to be important. So again, this is an area where one has to be careful, because if one is looking at only periodic sources and one has very good data so that the period determination is very easy or proper, then it is perfectly fine. Otherwise, one may have to temper a little bit as to which features one is using. And that is another area where we're going to be giving more attention, especially when it comes to completeness and coverage of features. Completeness is another thing that Nami had mentioned earlier, and that becomes quite crucial, again, especially when your training data sets are of different sizes. And so I'll like to finish by mentioning that we also have a few Zooniverse projects. One is related to stellar variability. It's called the Zwicky Stellar Sleuths. And here we were able to use a slightly different interface than the standard Zooniverse interface, because we wanted more interactivity. We wanted to show more metadata so you can do all kinds of things. And on the left-hand side, you see the field guide, which again, we are actively developing for more types of sources. And with that, I'll stop with this summary that we have been doing. We have started with a few variability types, but we are expanding that to more. And we have found that combining data from archives is incredibly powerful, and more people should really be using them rather than just staying with mostly their data. And our machines find many things, but building interpretability is one of the things that we are trying to focus on, and especially understanding the edge cases. And again, the ZTF DR4 is out there. Lots of low-hanging fruit are still there, which have not been plucked. So we are welcome to play around with that. With that, I'll stop. And if there's time, I'll be happy to answer any questions.
Okay, very much. Thank you, Ashish. Are there any questions to Ashish? We can start switching to another talk, but we can keep discussing if there are any questions. Pavel, please.
Yeah, thank you, Ashish, for this nice overview. I have a question. Could you say which method is the most powerful for finding transients or for classifying transients? Which one is the most effective?
By which method do you mean in terms of?
I mean the methods like Stetson, Skew von Neumann.
No, so I think that is the whole point. For different kinds of transients, different features are more useful. And that is where one needs to get to the details using better and better training sets, because it, after all, depends on the nature of the light curve, right? Meaning if it's going to have a sharp peak versus if there is going to be a single peak like a supernova that's over a long time, or whether there are going to be several peaks, some dips and so on. So whatever characterizes those quite well. And that is why I do not like to use a single classifier which simply puts together all the features. And the binary classifiers allow us then to pick specific features that are good for that particular class. And yeah, so that's what I would say.
Thanks.
I'm wondering also, but maybe it will be answered in Przemek's talk, how good these methods are in finding things which are never seen before.
Yeah, meaning outlier classification is one of the things that we are very interested in, and we have barely started that. We have found a few interesting things in terms of high amplitude variables, but again, because of the binary classifiers, the way it would work is that when you build something hierarchical from the binary classifiers, what you can get to is that any object that does not get classified as any of those objects with high probability is at least not in the set that you're already looking at. And that is where you need to build more classifiers. Of course, try to go to all the branches that is shown in the Nami and Laurent's figure. But yes, that is where one can also get to outliers.
Okay, great. Thank you, Ashish. And let's now move on to another ZTF related talk. Przemek Mróz from Caltech, please.
Hi, everyone. I'm Przemek Mróz. Currently, I'm a postdoc at Caltech working in the ZTF team. Today, I'd like to tell you about my work on searching for and studying gravitational microlensing events in the ZTF data, but also I would like to talk about possible synergies between ZTF and Gaia. So, as you've heard during the previous talk by Ashish, ZTF is one of the largest sky surveys worldwide. Currently, it observes the entire northern sky in G and R bands with a 2-day cadence. The survey is using a mosaic camera with a huge field of view of 47 square degrees. The camera is mounted on the 1.2 meter Schmidt telescope located at Palomar Observatory in California. And thanks to this enormous field of view of the camera that is an order of magnitude larger than that of other survey telescopes, we can scan the sky at a very high rate of up to 4,000 square degrees per hour, up to a depth of about 20.5 magnitudes. And what is also important, most of our observations and most of our data products are made publicly available to the whole astronomical community. And this includes ZTF alerts. So every time we see a star changes its brightness significantly, or we see a new transient appears in the sky, we release an alert, like 15 minutes, 20 minutes after the observation. Currently, alert packets include many information about the object, its coordinates, brightness, Big Bogus score, and so on. But the alert packets also include additional information, archival light curves, small cutout images of the object, and so on. In the future, we plan to include archival forced photometry of the object, as well as some machine learning-based classifications. So far, we have published over 300 million alerts. We are also publishing our light curves and images, and the most recent data release, the data release 4, was made public just little over a month ago in December. Data release 4 contains over 18 billion of images of the sky taken before 30th of June 2020, but it also includes over 6 billion light curves of individual sources that we observe. Every light curve contains from a few dozens up to 1,000 epochs. Usually it is between something between 200 and 400 epochs. And our most recent tool, the forced photometry service, you can request forced photometry of your favorite object at user-specified positions. This service is public, but you need to register for it via email. Once registered, you can submit requests for forced photometry. Currently, there is a limit of 100 requests per user per day. If you are interested in using this service, you can see more instructions at this URL. So today I'd like to talk about my work on searching for microlensing events in ZTF data. And usually when I think about microlensing, we are thinking about observations of the galactic center. So all major modern microlensing surveys, such as OGLE, KMTNet, MOA, they are all observing the galactic center, where the density of stars is the largest, and so the number of events is also the highest. However, we expect to see a large population of microlensing events outside the galactic center in the galactic plane fields. And from the scientific point of view, they are quite interesting, partly because microlensing events in the galactic plane have much longer timescales and larger Einstein radii than microlensing events detected toward the galactic center. So the plot here shows histograms of Einstein timescales of microlensing events detected in the bulge and in the disk. And those located in the disk are on average 3 times longer than microlensing events located in the galactic center. So these two features, longer timescales and larger Einstein radii, enable make the lens mass measurements much easier to obtain than for typical galactic bulge events. However, there is one big caveat. As we move away from the galactic center, the probability of microlensing and also the event rates are decreasing exponentially. So if we want to observe a large number of microlensing events in the plane, we have to survey a large area of the sky over 4,000 square degrees at a very high cadence of about 2-3 days. So ZTF is a perfect survey for such a task because it can observe huge areas of the sky at a relatively high cadence. And my work is to detect microlensing events in the ZTF data, either in the archival data, in the archival light curves, and also in the alert stream in the real time. Of course, the former task, finding microlensing events in the archival data, is much more easier because the information in the light curves is much larger than for the alert photometry. And currently, I'm using a machine learning-based approach to detect microlensing events in the archival ZTF data. I'm using neural network-based classifiers. Actually, there are two classifiers, one for single lens events and the other one for binary lens events. These classifiers take several light curve features as the input, and they were trained on the OGL data. And they are actually pretty good because they can correctly recognize over 98% of single lens events and about 80 to 85% of binary lens events. So, so far I've published a list of only 30 microlensing events that were found in ZTF DR2 data. Here are some example light curves, but I am currently working on the analysis of a much larger data set from DR4. So far I found about 100 events that they are just plotted here in this picture. However, I expect that there should be many more events hidden in the data, and currently I'm working on a new photometric pipeline that should allow me to find more events. But these numbers are roughly consistent with my expectations based on the galactic models. What I want to point out is that all of events detected by ZTF have very dense light, have very well sampled light curves with ZTF observations. They are sufficient to detect and characterize the events. But all of our events are concurrently observed by Gaia. So hopefully in a few years, we should be able to use Gaia time series astrometry to measure Einstein radii for at least some of our events, and as a result measure masses of the lensing objects and perhaps find interesting things like black holes or neutron stars and other things. I am also searching for microlensing events in the real time in the ZTF data. Usually, so here are some example light curves. Usually there's 1, 2 candidates each week. It of course depends on the time of the year, visibility of the galactic plane, and so on. Our microlensing candidates are spectroscopically observed either by using our own Palomar Caltech programs or as part of the LCOP project Omega, about which you will hear later from Etienne. And actually, it turns out to be really important because we found that there's quite a lot of contamination, for example, from AGNs behind it, like AGNs located in the galactic plane. They can mimic long time scale microlensing events pretty well. What I want to point out is that some of those events were independently alerted by Gaia, but because of the poor sampling of Gaia, the Gaia team could not recognize them as good microlensing candidates. So perhaps there is some room for like synergy with well-sampled ZTF light curves. I think Gaia Alert team could benefit from using ZTF this data to characterize the events. If you are interested in following up or observing of those microlensing events, you can check this website and talk to me. Happy to talk about So to sum up, I wanted to remember that ZTF is one of the currently is one of the largest sky surveys. We are observing the entire northern sky every 2 days. I'd like you to encourage you to use our data products, most of which are public. This includes alerts, our light curves, images, and photometric surveys. There are many possible synergies with Gaia and other teams. My current analysis, in my current work, I found over 100 events in ZTF data release for data. I hope to find more. The analysis is still ongoing. Hope to publish some results, say, within a few months. Thank you.
Okay, thank you very much, Przemek. Are there questions to Przemek? Kasia, please.
Przemek, thank you very much for a very informative talk. Could you say something more about the AGNs that are sometimes confused as microlensing events?
Yes, it was really surprising because we found a couple of very long, what appeared to be very long timescale events in the galactic plane, say 5 degrees within the galactic plane. And we took some spectra, and it turned out that these objects are AGNs at redshift 1.5. So it was a bit surprising because I did not expect to see AGNs there, but apparently they are. So it just tells you that it's really important to do some spectroscopic follow-up to be sure that these objects are indeed stars.
Thank you. We kind of detect also such events in Gaia. Well, mostly not in galactic plane, but outside of it. But still, they kind of look like microlensing events, and they have a good microlensing fit. So it was very surprising for me.
Yeah, so this could be some quasar microlensing.
Zosia, please.
Okay, first of all, well, nice to see you here, Przemek. And I have a question about those events that you detect earlier than Gaia, or the events that you detect and Gaia can't detect them. So is it only because of the cadence or the time, or are they also events that you detect better, for example, because you observe in different bands?
I think this is mostly because of the cadence. Usually, Kasia mentioned that the typical average cadence of Gaia observations is like 1 observation per month. And there are many events that have shorter timescales, so simply it's easier to find them with dense photometric coverage from ZTF.
Okay, thank you.
A quick question from Marcus while we have Etienne starting sharing his screen.
Yep. Hi, Przemek. I have a quick one as far as the binary classifier is concerned. Did you train the classifier based on OGL data with labeled binary events, known binaries from OGL?
Yes, that's correct. So all these classifiers were trained on real data, and I marked some events as binary, so that they were trained on real OGL data.
Yeah, and if I can quickly jump in, even the other binary classifiers that I mentioned in the previous talk, we tried to use as many available things from different data sets as possible, not trying to constrain it just to ZTF.
Okay, I will just mention that in the Black Hole Tom, we are actually automatically reading ZTF data, and that is very informative for many of the events we find in Gaia. So yeah, thanks for this. We don't need to follow. We don't need to do the follow-up ourselves if we have beautiful ZTF data. Okay, thank you, Przemek. We now move on to the last talk of the today's session from Etienne Bachelet about microlensing. Please, Etienne. Etienne, your screen disappeared. It was here before.
Hello? Do you see my screen?
No, not anymore.
Right. Is it good?
Not yet.
Ah, yes, sorry. Okay, should be good now.
That's better, yes.
Okay, thank you, Kash. So my name is Etienne Bachelet. I'm a postdoc at Las Cumbres Observatory. And today I would like to tell you about the Omega Key project, which started last summer. And it's a collaboration between Las Cumbres and various institutions worldwide and a lot of people from all around the world. And the main goal is the detection of cold planet and stellar remnants using the microlensing technique. And why microlensing planet detection is interesting. Here I describe two main reasons, in my opinion. So on the left graph, where you see in this planetary mass versus distance to the host normalized by the snow line, we can see that transit and radial velocity have made good census of the distribution of planets orbiting inside the snow line, which we refer as hot planets. And we have now a very good understanding of this planet population. But these planets are less efficient to planet orbiting beyond the snow line, and because their sensitivity decreases as orbital distance. But direct imaging and microlensing have their peak sensitivity for planets beyond the snow line. So we can see that all techniques are very complementary to understand the planet population. And also we know from planetary formation scenarios that the region around the snow line is important because it is expected to be the region where planetary core forms and planet accrete gas before potentially migrate. So understanding the planet population around the snow line is crucial to our understanding of the planetary formation mechanism. And the second reason is displayed on the right, where I plot the distance of planet detected from the Earth, and we can see quickly that only microlensing is capable of detecting planets several kiloparsec away from the Earth. And so to try to map the population of planets in the entire Milky Way, it seems microlensing is the best method so far. But as Przemek mentioned, so far microlensing survey have only focused to the galactic bulge, towards the galactic bulge, because the microlensing rate is the highest. And galactic bulge will be actually the main field of the Roman space mission, which it is expected that the microlensing survey will detect 1,500 cold planets. So as you can see in this left plot, when the Roman census will be finished, we're going to have a very strong understanding of planet population beyond the snow line, which will nicely complement the Kepler planet observation. But at the other side of the mass distribution of lens, since we don't need to observe the lens, the light coming from the lens in microlensing, we are also sensitive to stellar remnant and especially stellar mass black hole. And as Łukasz described in this paper, actually microlensing is an efficient method to complete the census of the black hole population that we can observe from a LIGO merger or from binary X-rays. And we can see from Łukasz candidates that it seems microlensing tend to disregard this hypothesis of a mass gap between massive neutron star and small mass black hole, but of course more observation are needed. So motivated by these two topics, we also live in an area where we have a fantastic whole sky mission that survey the entire sky and open a new potential for microlensing detection, such as Gaia or ZTF, and in the near future, LSST. But this the surveys, they have a relatively low cadence. Here on the left, I plot the first year of ZTF observation, and we can see that most of the fields have a cadence of few points per week, which can be not enough to catch a small planetary anomaly of duration of a few days. So And here it's a prediction of LSST microlensing detection rate in log scale per square degree per year. And it is clear from this plot that LSST has the potential to detect thousands of events every year. But again, we know that LSST cadence will be roughly 4 points per week, so which can be not enough to have a very good model of the lensing parameters. So the Omega project intends to ensure dense photometric and spectroscopic follow-up of the most promising microlensing event detected in by this survey. And it is a collaboration between Las Cumbres Observatory and several institutions. And we are always partnering with the AEON project, which is a project to make a network of various telescopes from LCO as well as Gemini and SOAR. And our basic strategy is separated in two. So first, we want to ensure a dense photometric follow-up in SDSS-I and SDSS-G with various modes. So each event have a regular daily observation for most of events. And as soon as events get highly sensitive to planets, we increase the observation to a 30-minute cadence. And in case we catch an anomaly, we increase the cadence to a very high cadence to try to catch this planetary anomaly. And for the spectroscopic, we try to obtain at least 2 low resolution spectra to try to disregard contaminants. And if it's bright enough, we can also trigger high resolution NOS spectra. So the Omega Q project rely on a core system which is called the Microlensing Observability Platform, which is a TOM toolkit database coupled and deployed on an Amazon web server. And the main goal of MOP is first to harvest all events coming from all of the survey, such as Ogle-MOA traditional microlensing survey, but as well as ZTF and Gaia. And we do an harvest every day. And we are also constructing the infrastructure to be able to harvest from LSST via brokers such as Antares or Think. As soon as the event are harvested, they are automatically fitted using PyLima, and the capability from AWS, we can use the possibility to parallelize massively on Amazon server, which we do. And this is what it looks after the fits. We obtain Pashinsky parameters from all events, from which we can compute what we call a tap priority, which is obtained from formula in Dominic et al. And Undermark et al. And based on this tap priority, we can adjust our observing strategy. And last step is to resubmit observation as needed. So observations are triggered automatically through the LCO network, and we can also trigger manual observation through the AEON system. And as I was building this talk, I was looking for some example, and this event Gaia 20 AHR was alerted 4 days ago. And actually the MOP ingested 1 day after, and automatically trigger observation. And we were able to obtain our first image of follow-up 4 hours after the MOP was aware of this event. And now I will conclude my talk with some example. I would like to speak about Gaia 20 BOF, which, as you can see, shows some sign of anomaly on its peak. And the most probable models tends to high massive planet or brown dwarf companion. So I think it's the first Gaia planetary candidate. So pretty exciting. And here it's the Omega observation from for the Gaia 19 DKE events that we already discussed in this meeting. So I will not go too much into details. But to conclude, I would like to invite everyone to contact us to know if we have data, because we observe a lot of events. And if you want to collaborate, we are happy for collaboration. So thanks.
Okay, thank you, Etienne. Are there any questions to Etienne? It's late here, and at least in Europe, and people are getting tired, but Chris is not tired. So Chris, please.
Thanks. Hi, Etienne. So I just wanted to clarify, you shown the plot for LSST, and mentioned the cadence, and that it's actually the event rate is very high, right? So this is just not the fitting the model, but just the detection of the outlier, or what?
You mean this plot here?
Yes, yes, yes.
So this plot is from Sadijan and Radek, I believe, where they try to estimate what will be the number of detectable events that LSST will find.
Yeah, exactly. So I wanted to ask what detectable means. So how do you know it's microlensing event if it's if you can't really fit the model?
I think it's detailed in the paper, but they disregard all events where their model of PSPL was not constrained enough. So I will say it's pretty conservative.
Okay, thank you.
I have a question regarding your TOM. I understand that your TOM is so clever that it decides on its own, right? What to observe and what not to observe.
Yes, so the idea of the MOP is to make all the steps automatically to from harvesting to fitting and try to observe. Yes, and he submit as according to several modes as I described in the talk. But as soon as the tap priority getting very high, trigger priority observation to try to catch planets.
So far, how was it performing? Was it kind of a good replacement of a human, an experienced human?
So this is we are checking actually the result of this, since the MOP implementation was just made at the time of the start of the key project. The start was a bit shaking. But we now believe that it works as expected.
Cool, great. Michel Denefeld has a question.
Yes, I was wondering what are your needs in low-resolution spectroscopic follow-up? What do you intend to do to classify the lensing star, or is low resolution enough?
So low-resolution spectra can help for some events to have the source parameters, source distance and source type, but mainly it is used for contaminant checking for contaminants such as Przemek described, for example, such as AGN or CV or some stuff like this. But to have a very detailed understanding of the source, it's better to have NRES spectra or X-shooter or even LBT Pepsi, for example.
Yeah. Okay. Thank you.
Okay, since I don't see any more questions, so I would like to thank all the speakers of today's session, the day 3 of our Gaia Science Alerts workshop. I thank you all, and I invite you to join us tomorrow. Tomorrow we start at 10 a.m. Polish time, so you can compute it to your time zone. And as usual, the talks will be transmitted and recorded on YouTube. Today's session is also already available on YouTube. And also I will remind you about the Slack channel and WonderMe room, where we can meet anytime, any time zone, to have more discussion and get to know each other a little bit better. So thank you all. Have a good night, have a good day, and see you tomorrow. Bye.
Bye.
Thank you, everybody.
Thanks,